The paper, titled, Dynamics of Semiflexible Ring Polymer in Chiral Brownian Particles Bath, explores the dynamic behavior of a ring polymer immersed in a bath of highly concentrated chiral Brownian particles. The study aims to investigate the conformation and motion properties of polymer macromolecules in Brownian particle systems. The authors use molecular dynamic simulations to analyze the effects of the chiral Brownian particles on the ring polymer. They find that the particles surrounding the chain drive the ring to deform, resulting in a torque that drives the ring to rotate in one direction. Interestingly, the relationship between the rotation speed of the ring and the angular velocity of the Brownian particles is not monotonically linear. The rotation of the ring initially increases, then decreases as the angular velocity of the Brownian particles increases. These findings provide a theoretical framework for understanding the deformation and motion properties of ring macromolecules in active particle systems. The study also highlights the importance of considering the influence of chiral Brownian particles on the behavior of polymer chains. The paper discusses the relevance of this research in the broader context of active Brownian particles and their potential applications. Self-propelled Brownian particles, or micro-swimmers, are active particles that exhibit directional movement and can obtain energy from their surroundings. Understanding the behavior of active particle systems and their interactions with polymer macromolecules has implications for various fields, including biophysics, materials science, and nanotechnology. The introduction also references previous studies that have investigated the random motion of nanoscale objects in bacterial baths, as well as the spontaneous unidirectional motion induced by bacterial baths in nanofabricated asymmetric devices. These studies demonstrate the potential for using active particle systems to drive directional motion and rotation. The introduction also mentions studies on the deformation and elastic properties of linear and ring polymers immersed in active particle baths, highlighting the need for further research on the conformation and motion properties of ring polymers immersed in chiral Brownian particles. Overall, the introduction provides background information on the topic, outlines the research objectives, and highlights the significance of the study in the broader scientific context. The figure shows a schematic description of the simulation system of a polymer ring chain immersed in rotating Brownian particles. The blue ring represents the polymer chain, while the green particles represent the rotating Brownian particles. The figure illustrates how the particles cause the polymer chain to deform and impose a torque that drives the rotation of the chain. This figure provides a visual representation of the system under investigation and sets the stage for understanding the subsequent results. This figure presents screenshots of the simulation of the polymer ring chain in a bath of rotating Brownian particles with different angular velocities. Omega_particle panel A shows the case where omega_particle equals 0. Resulting in the aggregation of particles around the polymer chain and the deformation of the chain into a dumbbell-like shape. Panels B to D show the cases where omega_particle greater than 0, leading to counterclockwise rotation of the particles and consequent clockwise rotation of the polymer chain. The screenshots demonstrate the dynamic behavior of the system and provide visual evidence of the deformation and rotation of the polymer chain induced by the rotating Brownian particles. This figure presents the results of the rotation analysis of the polymer chain. Panel A shows the rotation angle beta t of the polymer chain at different time points, indicating that the rotation angle gradually increases over time. Panel B shows the absolute value of the mean angular velocity of the polymer chain, omega_sr, as a function of the angular velocity of the Brownian particles, omega_particle. The plot reveals that omega_sr initially increases with omega_particle, indicating an acceleration of the rotation of the polymer chain. However, for higher values of omega_particle, omega_sr starts to decrease, indicating a slowdown in the rotation of the polymer chain. This figure highlights the non-monotonic relationship between the rotation speed of the polymer chain and the angular velocity of the surrounding Brownian particles. This figure presents the results of the deformation analysis of the polymer chain. Panel A shows the prolateness parameters, p, of the polymer chain as a function of time. For omega_particle equals 0, the prolateness parameter transitions from 1 oblate shape to -1 prolate shape over time. However, for omega_particle equals 0, the prolateness parameter remains close to 0 throughout the simulation, indicating a circular shape of the polymer chain. Panel B shows the average prolateness parameter, less than p greater than, of the polymer chain as a function of omega_particle. It shows that for omega_particle equals 0, the polymer chain exhibits a prolate shape, but for omega_particle equals 0, the polymer chain maintains a circular shape. This figure provides quantitative evidence of the deformation of the polymer chain induced by the rotating Brownian particles. This figure presents additional analysis of the deformation of the polymer chain. Panel A shows the bond angle, θ_I, between two consecutive bond vectors of the polymer chain for omega_particle equals 0 and omega_particle equals 0. It demonstrates that for omega_particle equals 0, the bond angles exhibit a V-shape pattern, indicating a cigar-like shape of the polymer chain. However, for omega_particle equals 0, the bond angles oscillate around 172 degrees, suggesting a circular shape of the polymer chain. Panel B shows the curvature throughout the polymer chain for omega_particle equals 0 and omega_particle equals 0. It reveals that for omega_particle equals 0, the curvature is almost 0, indicating a circular shape of the polymer chain. These additional analyses support the findings of the deformation analysis and provide further insights into the conformation of the polymer chain. This figure presents the distribution analysis of the Brownian particles around the polymer chain. Panel A shows the radial distribution functions of the Brownian particles around the polymer chain for omega_particle equals 0. It shows a peak at a distance of 1 sigma, indicating that the particles tend to aggregate around the polymer chain. Panel B shows the average number of neighboring Brownian particles near the polymer chain, less than n greater than, as a function of omega_particle. It demonstrates that as omega_particle increases, the number of particles near the polymer chain decreases, indicating a reduced aggregation effect. These results provide insights into the distribution of the Brownian particles around the polymer chain and their interaction with the chain. This figure presents the torque analysis of the polymer chain. Panels A and B show the torque at different positions of the polymer chain for omega_particle equals 0 and omega_particle equals 0, respectively. The colors represent the sign of the torque, with cyan representing negative torque and other colors representing positive torque. It can be observed that for omega_particle equals 0, both positive and negative torques are present, resulting in an indeterminate rotation of the polymer chain. However, for omega_particle equals 0, positive torque dominates, leading to a slower rotation of the polymer chain. This figure illustrates the role of torque in driving the rotation of the polymer chain and its dependence on the angular velocity of the Brownian particles. Overall, these figures provide a comprehensive understanding of the dynamic behavior of a ring polymer immersed in a bath of chiral Brownian particles. They demonstrate the deformation and rotation of the polymer chain induced by the particles and highlight the influence of the angular velocity of the particles on these behaviors. The distribution of the particles around the polymer chain and the torque exerted on the chain are also analyzed, providing further insights into the underlying mechanisms. These findings contribute to the understanding of the conformation and motion properties of polymer macromolecules in Brownian particle systems. The paper investigates the dynamic behavior of a semiflexible ring polymer immersed in a bath of chiral Brownian particles using molecular dynamic simulations. The study finds that the chiral Brownian particles around the ring polymer drive it to deform and produce torque, causing the ring to rotate in one direction. The relationship between the ring's rotation speed and the angular velocity of the Brownian particles is found to be non-monotonic. As the angular velocity of the Brownian particles increases, the rotation of the ring initially increases and then decreases. These findings provide insights into the conformation and motion properties of polymer macromolecules in Brownian particle systems. The study also demonstrates the importance of particle concentration and chain rigidity in influencing the deformation of the polymer. The research contributes to understanding the behavior of ring-shaped biological macromolecules in active particle systems and sheds light on the microscopic physical mechanisms of their rotation. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.